Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We've seen that the Galois group of a polynomial with a complete root set R of size n in some splitting field is isomorphic to a transitive subgroup of the symmetric group Sn. We've also seen that the Galois group of the general polynomial of degree n is isomorphic to Sn itself. There is a special symmetric function of the roots of the polynomial known as the discriminant that provides a tool for determining when the Galois group is isomorphic to a subgroup of the alternating group An. In other words, when the Galois group consists strictly of even permutations of the root set. So let's take a look at that now. Here's the definition. Let P of x be a polynomial over F with complete root set R in a splitting field E. The discriminant of P of x in, that should be E. It's amazing how often I make typos. I don't know. Anyway, in E is this quantity denoted by capital delta. It's a product of the squares of the differences of the roots, Ri minus Rj, I less than j. Now this is symmetric in the roots of P of x. And so Newton's theorem tells us that this quantity delta, the discriminant, is in fact a polynomial in the coefficients of P of x, which means it lies in the base field, F. Also, delta different from 0 would imply that P of x is a product of distinct, separable polynomials. In other words, delta not 0 means that there are no multiple roots, but we didn't say P of x had to be irreducible, so the best we can say is that it's the product of distinct, separable polynomials. And so the splitting field E is separably generated over F, which, as we have seen, implies that the extension is separable and therefore Galois. It's normal because it's a splitting field extension, and separable because assuming delta is not 0. So in this case then, the Galois group has the property that its fixed field is the base field F, because we have a finite Galois extension. Now let's take lowercase delta to be the square root of the discriminant. And there are two square roots differing by algebraic sign. It doesn't matter which one we take, really. Since each transposition of the roots will send delta to negative delta, it follows that any permutation sigma in the Galois group, permutation of the roots, satisfies sigma of delta, little delta, is negative 1 to the power delta, to the power sigma, little delta. And this is a common notation, as we saw in the group theory lectures, that for the sign or signum of the permutation sigma. And it's defined this way. Negative 1 to the sigma is 1 if sigma is an even permutation, and negative 1 if sigma is an odd permutation. So, the location of little delta with respect to the fixed field, the Galois group, can give us some information about the parity of the permutations in the Galois group. So in particular, if delta is 0, now this could be either delta. If capital delta is 0, so is lowercase delta, and conversely. Or if the characteristic of f is 2, then sigma delta will always equal delta. And so we learn nothing, because it tells us little delta is always in the base field f. So that's not helpful. So let's assume that the discriminant is non-zero, and the characteristic of f is not equal to 2. Then this equation shows that sigma fixes delta, this is little delta now, if and only if sigma is an even permutation. Okay? So sigma of delta is delta if and only if the sign of sigma is 1, if and only if sigma is even. So little delta belongs to the fixed field of G, which is f, if and only if G contains only even permutations. And here it is in symbols. Little delta is we know capital delta is in the base field. Little delta is in the base field if and only if the Galois group is a subgroup of the alternating group. So, if little delta is not in F, the base field, then the Galois group has to contain at least one odd permutation. But as we saw in the group theory lectures, and it's really not that hard to see, I'll leave it for you to ponder, that if a subgroup of the symmetric group Sn contains an odd permutation, then the subgroup has even order, and exactly half of its elements are even, then of course the other half are odd. So it's a 50-50. A subgroup of Sn is either completely contained in the alternating group An, or it's half in and half out of the alternating group. So we can say that in the following way: little delta is not in the base field if and only if the index of the Galois group over the even portion of the Galois group is 2. Now, we're dealing here with a finite Galois extension, so all the elements are closed, and we can take fixed fields here, and so delta is not in F if and only if the degree of the fixed field of G intersect An over F is 2, but the degree of F with delta adjoined over F is 2, and F with delta adjoined is contained in this fixed field, and so this degree is 2 if and only if F with delta adjoined is equal to this fixed field. And so ultimately we arrive at delta, little delta now, not in F if and only if when you adjoin little delta to F, you get the fixed field of the even permutations in the Galois group, the even portion of the Galois group, you might say. So we have two results here. When delta is in F, the Galois group contains only even permutations. When delta is not in F, another way to say that is that F with delta adjoined is precisely what fixes the even permutations. So here is a summary. Let F be a field with characteristic different from 2. Let P of X have degree n and splitting field E. And let little delta be the square root of the discriminant, either one. Because we're only interested in the location of little delta with respect to a field, so delta, little delta, negative little delta will have the same membership. Okay. So if the discriminant is 0, if and only if P of X has multiple roots in E, so capital delta, the discriminant, is non-zero, then the following hold. G is isomorphic to a subgroup of the alternating group if and only if little delta is in F. That's this statement here. And G is isomorphic to a subgroup of Sn that contains half-odd and half-even permutations if and only if little delta is not in F, and moreover, little delta is not in F if and only if the fixed field of the even permutations in G is this quantity, F with little delta adjoined. Okay, this may seem a bit abstract at the moment, but the usefulness of this theorem comes from the fact that the discriminant, capital delta, can actually be computed without knowing the roots of the polynomial. And that's quite remarkable. Well, this follows from the fact that little delta is up to algebraic sign the van der Maan determinant of the roots, and that's what this looks like. If you've studied differential equations, you're familiar with this determinant. If you multiply this determinant by its transpose, you get capital delta, the discriminant, is this determinant where the ui's are these quantities which are symmetric in the roots. So Newton's theorem tells us that because these are symmetric in the roots, they're polynomials in the coefficients of p of x. In other words, they're polynomials in known quantities. And as we've discussed, Newton's theorem provides us with an algorithm for actually computing these quantities u sub I directly from the coefficients of the polynomial. So that's how we can get the discriminant even if we don't know the roots of the polynomial. Now, of course, just because Newton's theorem does provide the algorithm I just mentioned for computing the discriminant doesn't mean that that's easily done. So let's compute the discriminant of a cubic, and you'll see what I mean. I'm going to go through this. I'm not going to go through all the algebraic details, all the arithmetic details, but I'll just kind of go over it quickly. So here's our cubic. It's monic. Let's say it has roots R1, R2, and R3. We don't know what they are, but we'll denote them by R1, R2, and R3. Now, the elementary symmetric polynomials in the roots are related to the coefficients in this way we've seen before. So the discriminant is this product, and the square root of the discriminant is this product, which can be written this way and denoted by capital R minus capital S, where capital R is this expression and capital S is this one. So delta is the quantity R minus S squared, which can be written as R plus S squared minus 4RS. Now, R plus S can be written in terms of the elementary symmetric functions or polynomials as follows. R plus S is all of this, which then is this expression in terms of the coefficients. And R times S is this product, which can be written this way. Doesn't look very promising at the moment, but the sum of the cubes of the roots can be written this way, and it is expressed in terms of the coefficients because this is symmetric in the roots. Making the substitutions indicated here gives us this expression, which is also a polynomial in the coefficients, and so r times s is now this polynomial in the coefficients, and so finally delta is this. Okay, now you see why I didn't go through all the algebra with you step by step. You can do it yourself if you want. Have fun. In any case, the discriminant of the cubic is this rather unpleasant looking expression. Well, let's see how we might use this then to understand to do a complete analysis of cubic polynomials. And again, we're assuming the base field has characteristic different from 2. So here's our polynomial. Well, let's say the roots are r, s, and t, so I don't have to deal with all the subscripts. And splitting field E, Galois group G. Of course, p of x is irreducible if and only if none of its roots lie in the base field. And that's particular to cubics, but it's going to be a big help. If the discriminant is 0, we know that p of x has multiple roots. If p of x is irreducible, then it's inseparable by definition, irreducible but with multiple roots. And there was a theorem way back in chapter 1 that tells us then that the characteristic of f is a prime and that p of x has the form q of x to the p. P is the prime here. So the characteristic has to be 3. There's only one root then of multiplicity 3, and so over the splitting field, p of x has this form. The Galois group is therefore trivial because alpha must be fixed by the elements of the Galois group. The degree of E over F is 3. So in summary, instead of capital delta equals 0, I can say small delta equals 0. It's the same thing, it's equivalent. So if little delta equals 0 and p of x is irreducible, then we know characteristic of f must be 3. P of x has no roots in f. It has this form where alpha is, of course, in a splitting field, but not in f. Galois group trivial, degree of extension, splitting field extension 3. Okay, there's a bunch of these coming. Now, p of x is reducible and has multiple, it has multiple roots, so it's not inseparable because separability applies only to irreducible polynomials. So p of x either has this form where the root a is in the base field, or it has this form, x minus a quantity x minus alpha squared, where a is in the base field but alpha is not in the base field. Okay. Actually, yeah, it could be, it's anywhere in E. The coefficients of p of x lie in f, so alpha also must lie in f, because when you multiply this out, a plus 2 alpha is in f, and so since a is in f, so is alpha. So we do know that alpha lies in the base field. So p of x splits over f. So when little delta is 0 and p of x is reducible, it splits over f, has either a double or a triple root. So I replaced alpha here by b. A and b lie in the base field. Galois group is therefore trivial, and the extension has degree 1. Now we come to cases where delta is not 0, so we have no multiple roots. P of x is P of x is either separable or a product of separable polynomials. In any case, the extension here now is both normal and separable, so it's Galois. P of x might be reducible, and delta might be an f. In that case, G is isomorphic to a subgroup of the alternating group A3, which has order 3, and so the Galois group is either trivial or isomorphic to A3. But since P of x is reducible, it has at least one root in the base field, which means that the degree of the splitting field extension is at most 2, and so it has to be 1, because it can't be 3. And so the Galois group is trivial. And so here is the summary. We have P of x splitting over the base field. P of x reducible in delta, little delta, not in F. In this case, G is isomorphic to a subgroup of S3 with an equal number of even and odd permutations. So G has order it's even order dividing 3 factorial, or 6, so it's 2. So over E, P of x splits this way: one root in the base field, the other 2 roots not distinct because delta is not 0, and not in the base field. So what does the Galois group look like? Well, it's got the identity, and it has to swap the 2 roots, alpha and beta. Those are the 2 possibilities. Either alpha is sent to itself and beta to itself, that's the identity, or it's a transposition that swaps these 2 roots. A is fixed because it's in the base field. That is isomorphic to S2. So the degree of E over F is 2. And here's the summary. Little delta in F, P of x reducible. P of x does not split over F, but over E it splits. Alpha and beta are distinct roots in E but not in F. G is isomorphic to Z2, A2, A3. I'm sorry, A2. What did I say over here? It's isomorphic to a subgroup of S3 with an equal number of even and odd permutations, and so it has size 2, so that's Z2. Here we go. I called it S2 here. Okay, same thing, S2 and Z2. The degree of E over F is 2. P of x is irreducible and delta's in F. In this case, G is isomorphic to a subgroup of A3, the alternating group, because delta is in the base field, so G is either trivial or it is isomorphic to A3 itself. But the irreducibility of P of x implies G is not trivial. And so G is isomorphic to A3, and therefore its size and the degree of the splitting field extension is 3. P of x splits over the splitting field 3 roots belonging to E but not F, and distinct. So I should have said that here, distinct, because capital delta is not 0, so we no multiple roots. Okay, and so as a matter of fact, if we adjoin one root to F, we will get the splitting field. Okay. So this is what the Galois group looks like. It has size 3, the identity. Every element has to have order dividing 3. We have this 3 cycle, and its square or its inverse, same thing. So this is the summary. In this case, delta is in F, but not 0, because capital delta is not 0. P of x is irreducible. Then it has no roots in the base field. But it has degree 3, so if we adjoin a single root, this will be the minimal polynomial of that root. And so that's why once we adjoin alpha, we have e of degree 3 over f. I'm sorry, we actually have f with alpha adjoined to degree 3 over f, and therefore it's equal to the splitting field. Okay. G is isomorphic to A3, and the degree of e over f is 3. How many more do we have to go? Just one more. Okay. P of x is irreducible, and delta is not in F, so P of x is separable. Okay. G is isomorphic to an even order subgroup of S3, so the order of G is at least 3, because P of x has degree 3, and the order of G is the same as the degree of the splitting field extension, and it divides 6, but the order of G is even. That only leaves order of G equals 6. So G is isomorphic to S3. P of x splits no roots in the base field. If we adjoin 2 of these roots, we will get the splitting field, and that's the summary here. So we have the whole story. And here is the theorem. I just basically cut and pasted all those different cases. Okay. So, without knowing the value of the roots of a cubic, we can learn quite a lot about the nature and location of the roots. As a matter of fact, in the case of real polynomials, we can learn more about the roots by looking at the sign of the discriminant, capital delta. A real cubic either has 1 real root and 2 non-real complex conjugate roots, or it has 3 real roots. And in the former case, little delta is this rather ugly looking thing, but it is, when we square this, we get something less than 0, negative. So the discriminant is negative. In the latter case, the discriminant is non-negative, and it's 0 if and only if the roots are not distinct, if there's a multiple root. So for a real polynomial of degree 3, discriminant less than 0 if and only if P of x has exactly 1 real root, delta greater than 0 if and only if P of x has 3 distinct real roots, delta 0 if and only if P of x has real roots, at least 2 of which are equal. Of course, you may be thinking, well, I can do this from my high school analytic geometry. I can just high school calculus. I can just draw a graph here, get the local maxima and minima, and figure this out. That's certainly true. Here's an example, a cubic over the rationals. Any rational root of this must be plus or minus positive negative 1, but these aren't roots. And so P of x is irreducible over the rationals. The discriminant is equal to 49, which is positive, so P of x has 3 real but non-rational roots. Little delta is rational, so its Galois group of the polynomial is isomorphic to A3, and its splitting field consists of Q with any one of the roots adjoined. On the other hand, for this polynomial, it's irreducible and its discriminant is negative. Its square root then is not in the base field, and so P of x has 1 real but non-rational root, cube root of P, and 2 non-real roots. The Galois group is isomorphic to S3, and this is a splitting field, and I'll let you figure that out. This polynomial, delta is 81. P of x is irreducible over the rationals, and so little delta is equal to 9, which is rational, so the previous theorem, theorem 43 tells us that G is isomorphic to A3. So splitting field for P of x over Q has degree 3 and is generated by any one single root.